Sets are collections of objects. And sets are denoted with capital letters. And the representatives from each set are denoted by lowercase letters. So, for example, we might have set A, and then if we wanted a representative from set A, we would use a little a, and the notation that says that an element is in a certain set is this funny looking sort of E type thing here. Looks sort of like that. And so that this means A is in the set big A. And then what would we do if we wanted to denote the fact that little a was not in set big A? What would we do? Not in, yeah. It's a very handy thing. You just make a sort of a forward slash through anything here to denote that it's not. So A is not in set big A. And so let's look at this set here. Set P is the set of U.S. presidents. Who can name me one element in set P? Well, Obama, Leo, Barack Obama is in set P. Who else is in set P? Yeah, GW is in set P. All right, name someone who's not in set P. Who? Sarah Palin. SP. Not in P. Who else? Me. You. Not in P. So there we go. All right. So that's the use of sets. Now, there are several ways to sort of think about sets, and sets have various different properties. A set could have no elements, a finite number of elements, or an infinite number of elements. Right? What would be a set with no elements? You can just think of some description. Anyone have a good description? How about this? A set of people on Mars. All right. How many people are on Mars? How many? Many? Not many. Not many. No. There's nobody on Mars. So that would be the empty set. What else? The other one I have in my notes is set of female U.S. presidents. That's no elements. What's an example of a set that has a finite number of elements? Finite means limited. Right? Think opposite of infinite. Right? Infinite is unlimited. Finite would be limited. What's a finite number of a set with a finite number of elements?
Students in this class.
Yeah, students in this class. Yeah. So we could create a set of each and every one of you, and then that's finite because there's only like 20 of you. Yeah.
Judges, Supreme Court judges.
Let's see. Supreme Court justices. U.S. Supreme Court justices. Yeah, even more specific. Okay, those are good sets. All right, what about a set with an infinite number of elements?
We do like stars in space. Would that be an infinite?
It's hard to say, isn't it?
Yeah.
We don't know. We know the universe is expanding, but we don't know. We don't know if there would be an infinite number of stars or not. Yeah.
Just say like greater than 0.
What greater than 0?
Set greater than 0.
The numbers greater than 0. Yeah. In fact, let's do integers. Positive integers. Positive integers. So the positive integers are whole numbers greater than 0. That starts with 1, and goes 2, 3, 4, etc. What's the largest positive integer? There isn't one. They keep going, and so there's an infinite number of elements there. Okay. Looks good. All right. There are basically two ways to represent sets, by rule and by listing. Let's start with by rule. Okay. And I'll start with some of these examples that we already had and maybe throw in a few extra ones. Let's say that set P is, again, the set of U.S. presidents. The way you write a set by rule is you're going to give it the curly brace, right? So sets are normally denoted with curly braces if we're going to do the rule or the listing of them. You need to give me the prototype of the elements in the set. That's usually the lowercase letter that is the representative of the name of the set. So big P yields a little p. Okay? You don't always do that, but you should have a pretty good reason if you're going to go around that convention. Then we have a big vertical bar. Oops. And the big vertical bar is read as such that. Okay? So this is the set of little p's such that, and then you give me some verbal description of the elements that would be in your set. And in this case, it would be P is or was a U.S. president. And then you close the set. Notice how I incorporated little p in my description. Okay, that is sort of the whole point of the by rule. The rule that gets you into this set is that you are or was a U.S. president. Okay, let's try another one. How about big F? Big F is the set of little f such that F is or was a female U.S. president. And how about S is a set of little s such that S is a student in this class. And then, how about N, such that little n, such that N is a positive integer. All right, so those are some examples of the by rule. Every time you do a by rule, you got to have the prototype and then such that, and then you list off the rule there to write out the rule. Okay. Next would be by listing. When you do a listing, you just list each element that's in the set if you can. If you can't, you do some dots and call it good. So let's do each of these sets again, but now let's do them by listing. So P would be the set of, and we'll just try to do this in order, GW, George Washington. Who's after GW? Who is number 2?
John Adams.
John Adams. Number 3. Uh-oh.
Thomas Jefferson.
Yeah, DJ. And then who is number 4? Madison. And then number 5, Monroe. And we don't have to keep doing this. Number 6 would have been this guy. Yeah, John Quincy Adams. ... because there's too many to list here. And but then this is a finite set, right? There's only been so many presidents, and the current one is the last one, BO. So the ellipsis here indicates that we're leaving out some of the elements, but we've got a sequence going, we've got a pattern going, so we'd know how to fill that in. All right. How about F as the female presidents? What's in there? Nothing, right? So there's 2 ways to denote this. You either put up a set and you don't put anything in it. That is not my favorite, by the way. The other way to do it is to write this symbol. It's a circle with a slash through it. And this is called the empty set. The empty set is the set with no elements. Yeah.
Would you want us to put that symbol in between or by itself?
Yeah, by itself. If you put it in the braces, then what you actually give me is a set that has the empty set in it.
Okay.
Yeah. Yeah. Yeah, that's a good question. Yeah. Okay, S would be the set of students in this class. So, what's your name? Yeah.
Cullen.
What? Cullen? Cullen. And then, what's your name? Jonathan. Jonathan. And then, what's your name?
Vin.
It doesn't matter. Vin? Okay, that's fine. Whatever. It doesn't matter. And then that's it. You just list all the students in the class. And then lastly, for n, the set of positive integers. It will be 1, 2, 3, 4. This set is infinite. It doesn't stop. So we put the dots, and then we close off the brace. All right, so questions about the differences between by rule and by listing. Okay. Which of these sets has no elements in it? What's the set name? F. F has no elements. Which of these sets is finite? Finite. Finite. P and S are finite. Technically, F is finite too, but we've already covered that. And then which is infinite? N is infinite. Barack Obama is the 44th president? Yes? Yes? Is that right? I think that's right.
Something like that.
Reagan was 40. Bush won, 41. Clinton was 42. George W. Bush was 43. So Barack Obama was 44. How many elements are in P?
You just said 44.
It's not 44. It's not 44.
43.
It's 43. Let's go to the map. Oh. Us. Fantastic. List of U.S. presidents. Here we go. Here we go. Washington, Adams, Jefferson, Madison, Monroe, Quincy, Adams, etc. Until you get to right here. Grover Cleveland was number 22 and number 24. Because he didn't serve consecutive terms, he gets two different numbers. Which means there were actually only 43 different presidents. When you're in a set, you don't get listed twice. You're either in the set or you're not in the set, period. So if we had actually written out our list for the presidents, we would have listed Grover Cleveland only one time, even though he served two different non-consecutive terms and got two different numbers. Now, my favorite, of course, is Rutherford B. Hayes. Look at that guy right there. Look at that. Look at that beard. Look at that beard. There. Okay. There you go. That's your American history lesson for today. Okay. Next page. All right, go ahead and do example 3 with your partner. Denote the set S of all numbers x such that x squared is equal to 25 by rule and by listing. So you'll have two different answers. Okay? And it tells you what prototype to use. You need to use the prototype names. Okay, right out of your book. Yeah, this one's a little sneaky. It wants you to use X for the prototype. I thought it is just because it's like a solution set to an algorithm. This is one of those advances.
So instead of S,
Yeah, hang on. One more time. Yeah. This X is the prototype. Building up.
yeah,
The same exercise.
yeah.
Don't overthink this one. And you can basically read it off here. X such that x squared is 25. That one's right.
Second one is not right.
It's half right. Half right out. Half This is the prototype. This is the description.
No, you have to do
Oh, no, yeah, you're right. You don't have to do this.
We try to use the sign
So this is this one here.
When you do a business,
So this is
analysis, you don't do
yeah,
that.
you're right.
It's such that.
It says as is that. So he's put description X is the X. Okay, so.
5 is how we use
You mean,
So, you have to do X is.
I was just doing that.
No,
without. Okay, let's check it. All right, denote the set X of all numbers X such that X squared is equal to 25 by rule and by listing. If we do this by rule, then S is equal to the set of X. Now, this changes the convention because it's algebra. This is the way they write algebra sometimes. You use the variable that was given in the problem. It's X such that. Now, what is the condition for you to be in the solution set? When you get squared, you are equal to 25. So X squared equals 25. All right? And then by listing, what squared is 25? 5 and negative 5. And that's it.
Does it matter which one you list them?
No.
5, -5.
Now, being in a set is not dependent on order. Yeah. You just got to be in the set. All right, questions over that? Yeah. So don't overthink this. This says it right here. X such that X squared is 25. That's what you write. Okay? And then the listing, of course, you got to make sure you get all the answers. All right, so we've talked about sets. Now, if we want to take a portion of a set, we call that a subset. Okay? So the notation here is the following. A is a subset of B means the following. It means that every element in A is in B. Is in B. So a subset of a set is just any sort of sub-collection of some of the elements from B. Certainly I could use all the elements from B, right? I could use none of the elements from B, maybe. We'll need to talk about that. Or I could use a few of them, 1, 2, however many I want. Okay. Two sets are equal. The notation is the obvious notation here. A is equal to B. And that means that A and B have exactly the same elements. And then, of course, we have not a subset. How would you form not a subset? Yeah, take your subset symbol, put a line through it, and not equal, of course. So not A is not equal to B. So you could have that as well. All right. As it turns out, the empty set is a subset of every set. Now, how does that work exactly? In order to be a subset, the strict definition here is that every element in the left is in the set on the right. So if it were a subset, then we would have something that looks like this. We would have the empty set is a subset of B. And so every element here is also in here. Every element here has to also be there. Is that true? No. B could be presidents. The empty set is a subset of every set. You give me a set, the empty set is a subset of that set.
Why?
That's what you have to figure out. So how does this work? If every element here has to be over there, maybe we should rewrite this. But really, the way to rewrite this would be to say something like this. To say, if, let's call it X maybe. X is an element of the empty set. Then X is an element of B. That's what this really translates to, right? If X is in the empty set, then X is in B.
But how can there be an element in an empty set?
So what is a set for a set? You have to go back and define a set to understand whether or not something empty should be in a set.
No, we just use the same one we use. Collection of anything. Collection of objects.
So nothing is anything? Because
And, yeah, like the set of female presidents. That's a set. Just doesn't have anybody in it. Would you agree that the set of female presidents is a subset of the set of all presidents?
maybe.
Of all presidents.
All U.S. presidents, American presidents.
Oh.
American presidents. The set of all American female presidents is a subset of all American presidents.
Yes.
Right? I mean, the females would be part of it, and the males would be the other part, right?
But you could have anything and be a subset of American presidents.
Not everything. Take, for example, the set of cars made by Ford. That's not a...
So it always has to be quantifying or qualifying like element in order to be in the subset.
Yeah, it has to. To be a subset, it had to sort of originate from the original, right? So you could have a subset of models by Ford. Would be a subset of all models of all American cars.
But
Not of something else,
a European
right?
car.
Not of European car, or even something even more abstract. The set of I don't know, just the set of dorms on campus. I mean, this is completely unrelated. What's interesting though is that the empty set, which has no elements, is a subset of every set. Now you're onto something.
So you can put an empty set in anything.
The empty set is a subset of everything, every set. But how does this work? Why is this true?
Just a placeholder for the idea of the absence.
Mm-hmm.
It's just saying that if there's nothing in there, you can fit it into any category, really.
Yeah. But if X is in the empty set, then X is in set B. I just call it B, whatever, any set B. Do you believe this thing? Why?
Because there's nothing in the empty set.
Okay.
Because the
And
down to like the presidents, well, that's obviously in there because it's nothing.
Would it be related to yesterday talking about conditional? And if then the supposition of that?
What was the big point of that?
Well, it can't be false.
What?
It can't be false.
Which part of this is false?
The first part, I think the first part.
Vacuously true.
This is vacuously true. If X is in the empty set, empty set is empty. X is not in the empty set. So the first part is false. Therefore, the whole statement is vacuously true. So, yes. This is vacuously true. Very good. So that's how you use vacuously true in all this stuff. You create a condition where the first part can't possibly happen, which makes everything else fly. Okay. Very good. So you now know you can sort of think of it this way. Every set has two subsets. I should qualify that. Almost every set has two subsets. You have at least the empty set, and you have the set itself. All right? So the set of presidents and then the empty set. Those are at least two subsets, right? There's only one set that only has one subset. What set is that? So most everything else except for this set that I'm thinking of will have at least two subsets. Yeah, the empty set itself only has one subset, which is the empty set. If you have any element in there whatsoever, then you have the empty set, and then you have the whole set, and then you may have others as well. All right. Example number 4. I'm going to do I'll do one of these, and then I'll let you work with your partners. You're given the following sets. A is the set 1, 2, 3. B is the set 2, 3, 4. And C is the set of 1. Determine if each of the following are true or false. So the first one here is A is a subset of B. In order for A to be a subset of B, we have to have every element in A reside in B. Does every element of A also live in B? No. Which element in A is not in B? The 1. So therefore, this is false. All right, go ahead and complete the other 7 with your partner.
Oh, wait. Yeah.
And the C is the 81.
Leaving a subset in there. Because it was
Okay. What'd you get for B is a subset of A? That is false. Which element shows otherwise here? Which element is in B that's not in A? Yeah, the 4 is in B, but it's not in A, so that's a no-go. C is a subset of A? True. C is a subset of B? False. A is a subset of C? True or false?
True.
Try again. False. Yeah, this one is false. Every element in A is not in C. All right, the 2 is not in C and the 3 is not in C. how could you know that A could not possibly be a subset of C? Yeah, C only has one element, and A's got 3. That's not going to work. Yeah, you're trying to fit it into a small box. You can't do it. Same logic for B is a subset of C. That's a no-go. The empty set is a subset of B. True or false? True. And A is equal to C. That is false. All right. Yes?
The subset is equal to C. That's vacuously true, right?
This one is vacuously true.
Okay.
Yes. Yes. Okay. All right. So that's the basics of sets. Now what we're going to do is we're going to talk about union and intersection, complement, and we'll draw some Venn diagrams. So these are set operations. You're going to take two sets and you're going to combine them in some fashion. The union is denoted by A union B. Now, this is a pet peeve of mine, so pay attention. This is not a U. It is a union symbol. It is a cup. It looks a whole lot like a U, but it doesn't have a tail. Right? It's just this. So don't put the tail on it. It's not a U. All right? All right. Good. The union is the set of elements X such that the X is in the set A or X is in set B. So we're going to apply some of the stuff we did yesterday with logic, and we're going to shift them over to sets. So here we have X such that X is in A or X is in B. Intersection is denoted A intersect B, and it's the upside down version of the union symbol. Looks like an N. It's not an N, but that's how you remember it. X such that X is in A and X is in B. So in order to be in the intersection of a set, you have to be in both sets to start with. So these are the ones that the A and B have in common. They're in both A and B. To be in the union, you just have to be in one of them. Right? All right. Complement is denoted A prime. It's like an apostrophe. It's usually called a prime mark. Right? It's usually more slanted. Okay. And this one is the set of, now this is a little bit different, so watch this. This is X in the universe. Okay. We usually use the capital U to denote the universe. The universe is just the set of things that you are taking under consideration. Earlier we were talking about cars and things like that. We could have the universe of all cars. We could have the universe of all people. Right? That would be our universe. It's sort of a way of restricting our focus to what we are talking about. Such that, now complement means that you are not in the set you're talking about. So the complement of A is the set of elements that are not in A. Yeah, it's the set of elements that are not in A. Right? So A is a set of elements, and A complement are the ones that are not in A. But they're in the realm of what we're talking about, which is called the universe. Whatever that might be. Universe could be numbers, could be people, could be something else.
Okay, so A, complement part of it. X is a subset.
No, element of.
Element of the universe.
Such that.
But X is not
In A.
in A.
Right. So earlier we had the set of presidents. So the complement of the set of presidents, we're all in that. Because we're not presidents. We never were. That's what a complement is. What does complementation correspond to from yesterday's lesson on logic?
The negation.
It's the negation, yeah. This is the negation. This is the and, the conjunction. And the one up top would be the disjunction. Right. So they all have sort of logic logic counterparts here. All right. You want me to write down what the U is here? U is equal to the universe. All right. Let me draw some of the Venn diagrams. Venn diagrams are a way of expressing sort of the relationship with the sets. Okay, we're going to draw them sort of generically here. Let's start with union. Okay, so there's the universe, the box. And in here we would have a circle that represents A. So everything in that circle would be elements of A. And we could, put people in there. And they may overlap, and that's okay. So we have to draw that possibility. And then everything in this circle here would be the things that are in B. The union, A union B, is the set of elements that are in A or in B. So you could be in either one. Okay? And so what we normally do is we just color this in here, shade it in, or anything like that. So everything that would be shaded in the two circles there would be part of the union. Notice also that I shaded in this area here. If you're in this little piece right here, you're in both the A and in the B. And we talked about this yesterday. That's okay. Are you going to McDonald's or are you going to Taco Bell? Normally you just go to one of them. That's counter to the way math works with or. Or does not preclude the possibility that you are in both of them. Okay? So that is okay. That is union. Let's look at intersect. So here we have another universe. We have an A. We have a B. In order to be in the intersection, you need to be in both A and B. And where is that on the Venn diagram? It's right here. It's where the circles overlap. And that is all. So right here in this area is A intersect B. And that's it. And lastly, we want A complement. For A complement, I only need a one set, A. Right? Complement is not a two-set operation, it's just a one set. And A complement is the set of elements that are not in A. That would be everybody in the universe that is outside the set A. It's everybody else. Can y'all see the green? Okay. It's everything outside. Everything outside. All right. Any questions over Venn diagrams? Now, there are sort of two ways to work with Venn diagrams. You either work with the elements themselves, the elements from the sets, or you sort of denote how many things are in each portion of the Venn diagram. We're going to start by doing the first, and then we'll work our way up to doing the second piece later on. All right. So let's look at example 5. Example 5 says, let A be 1, 2, 3, B is 2, 3, 4, and C is 1, same as before. And the universe is 1, 2, 3, 4. Find each element and find each set and draw the Venn diagram. So I'll do one, and then I'll let you work with your partner on this. The first one is A intersect B. Intersect means which one? And, or complement? It's and, right? We want it to be, it has to be in both. So which elements are in A and in B? Yeah, 2 is in there, and 3 is in there. 1 is in A, but it is not in B. 4 is in B, but it's not in A. So the only elements that are in both A and B are 2 and 3. All right, go ahead and complete that with your partner, and then draw the Venn diagram here on the side here. Right here. Draw it nice here. That's not good. Zero is not an element, because so you can't even use zero. Okay. If you're trying to express an empty set, that's a set by itself. But I don't think you want to. Well, yeah, and you wouldn't do that either. That's sort of a different thing. Set, empty set. That's a set that continues. If you want to use set, you would just write empty set. But it's not.
It's not empty set.
I don't think so.
No, but this is the not NC. So you put the one that is an NC. So one is.
Well, the universe is only 1, 2,
So
3.
you put 2, 3, 4. Yeah.
Yeah, and it can't be A,
But
it
if
can't
it's
be
not,
B.
I think
What is the or what is the last one?
then it's missing.
Everything.
What's not in A? 4. What's not in B? 1. And you're putting this. Yeah, that's over. So or is like a big old hay bale. You're just picking up everything.
So what's not in C?
But it's the other one that's supposed to be. There's one, isn't in E, but it's in A.
It's okay.
That's okay?
Yeah, if it's or, you just pick everything up.
Okay, so what's not in C?
So like this one, what do you get for this one?
1, 2, 3, 4.
Yeah, that's good.
What isn't? Oh, okay.
Because 4 was in this case, right?
It's like the opposite.
Yeah, if it's intersect, then it's got to be things that are both aligned. But
So like here's that same question, but with
right, that would be easier. Number 4 is not the empty set. You'll need a third circle. Yes.
Okay, I did that.
The question is,
And if anything that's not, there's not in B, so it's anything besides 2, 3, and 4.
great question. Son, don't tell me that's great. It's a fantastic.
1, 2, 3, and 4. I just don't know how to write that.
Huh?
How would you write?
What? Oh, no. No, there's better ones there.
How would you write anything but 1, 2, 3, and 4? Like, do you put a procedure on them and then like put a little line in it?
You want to not use 1, 2, 3, and 4?
Yeah, for the.
Well, that's the universe. So that's the emphasis.
Well, one has a.
I thought you said the 4 is.
All right? Yeah. You need to do it.
So it isn't? Or is it?
It's not here. No, you're doing it. Why is this one causing so much problems? What did I do wrong? What did I teach y'all that? Why are y'all getting number 4 wrong? What did I teach y'all that was so bad?
I think it's just like a set.
What is this? Okay. You have to do the complementation stuff first, right? You're doing complements first? Yes? Yeah, complements come first. What is a complement? What elements are in a complement? Just the number 4, right? Because A is 1, 2, 3. And so we have 4. Union means we're going to pick up everything. So the answer has at least the element 4 in it, right? Because union is or. It's either in this one or that one, and so we pick them all. What is B complement? 1. So it's 4 and 1. So why did y'all think it was empty? I'm trying to figure out, because I must have said something that makes y'all think this is empty.
I was thinking it meant not.
Yeah.
It's just
Not.
So, like, because for the Venn diagram, we put not in A.
Uh-huh.
So I was thinking that it's what's not in A and what's not in third.
But see, you said and, right?
It's or.
It's or, right? So it's not in A or it's not in B.
So if it was and, they would both.
It's and.
It would be in B.
Yeah. Let's see. Maybe it's like this. You're going to have a party. What are some of these sororities? The Delta people, right? And then what's another one? Alpha people? Are there alphas? Is that a thing? I don't know. I'm just calling all 3 letters. So let's say you're going to invite people that are not alphas or they're not deltas. Do any alphas get to go? You're going to invite people that are not alphas or, mathematically, or not deltas. Do any alphas get to go? Yes. Yeah, the ones that are not deltas. Right. It's like, all right, how about this? Remember this riddle? There are 2 coins in my pocket. And the sum of the 2 coins is 30 cents. And one of them is not a nickel.
The other one is a nickel.
What are the 2 coins? Let me say it again. There are 2 coins in my pocket. The sum of the coins is 30 cents. One of them is not a nickel. What are the 2 coins? It's a quarter and a nickel. Because one of them is not a nickel. It's a quarter. This is the other part. All right, let's go ahead and do the answer. Did you draw the Venn diagram? All right, what is A union B? Okay, what's going on here? Oh, it's on oval. 1, 2, 3, and 4, also known as what?
Universe.
That is the universe. All right, what is A union C? So A union C, we pick up everything in A and everything in C, but we don't repeat. So we already got the 1, so we don't repeat it. And what is that? That's just A. You don't have to put these extra letters. You could just write it out. That's fine. All right, this one we already talked about. The things that are not in A is a 4, and the things that are not in B is a 1, and there you go. All right. C prime intersect B. What is that set? That's 2, 3, and 4. So the elements from C prime are the ones that are not a 1, which is the 2, 3, and the 4, intersected with 2, 3, 4. That is exactly 2, 3, 4. And what set is that? That's actually B itself. Okay. Here's A. Here's B. What elements go in? The easiest part is the middle. What elements go in the middle? 2 and 3. I'm going to denote these with dots. So dot 2 and dot 3. And then, what other element is in B? Does 4 go in the middle? No, because 4 is not in the intersection. So it goes on in the part of B that's outside of the intersection. All right, what elements are in A? 1, 2, and 3. We've already done the 2 and the 3. Is the 1 in the intersection? No. So we put the 1 in A, but not in the intersection.
Wouldn't that also consider?
Yes. What is the relationship between C and A?
A prime is equal to C. Or that
All of C is an A.
All right, what's that called? That is a subset, right? When you have a subset, you draw that set entirely inside another set. And so this guy is C. Yeah. All right. Okay. So questions over this? We're getting to the heart of this stuff now. All right. Example 6. There are 20 students in class. 15 students have a dog, and 12 students have a cat. Also, 8 students have both a dog and a cat. How many students have only a dog? How many have only a cat? And how many have neither cat nor dog? All right, so the trick here is to draw the Venn diagram. Now this time, we are simply going to represent the elements inside the Venn diagram as the number of elements in that particular portion of the set. Okay? The items in the set would be student names. We're not going to list all these students. We don't even know who they are. They may be you, they may not be. And by the way, there is a notation for this. I'll show you the notation if it gets used. You do n of the set. Okay, so let's say that the D is the set of students with a dog. So n, little n, of D would be 15. So n stands for number of elements in the set. So n of D is 15. What is n of C? It's 12. What set would be the best way to represent this? Students that have both a dog and a cat. Is that Grant? Yeah, use the D and the C again. It's and, so it's what operation? It's intersect, yeah. So D intersects C is 8. All right, so let's put these in here. Here's D, here's C, this is the universe. Sometimes you'll see the U on this, sometimes you don't. It's a box, assume it's the universe unless you think otherwise. The easiest place to start with all this is in the intersection. So D intersects C is 8. So the 8 goes here. Now which one you want to do next? Dog or cat? You want to do cat next. All right. The number of elements, the number of students with a cat is 12. How many go here? 4. Because the whole circle represents all 12. I've already accounted for 8 of them, so there are 4 students that go out here. Same thing with the dog. There are 15 total students with a dog. I already have 8 of them. How many other students are there? 7. What else? Yeah, there's one more person who's in the universe that is outside of the dog and the cat sort of sections because of what information? Right there. There were 20 students in class. 7, 8, and 4 is 19. So there's one more person to be accounted for. That person is outside of the dog and the cat. Okay? So how many students have only a dog? 7. How many students have only a cat? 4. And how many students have neither dog nor cat? 1 student. All right, questions? All right, go ahead and do example 7 with your partner. Are we ready? Okay. Need to draw a Venn diagram. Oh, this could be exciting. I'm going to draw it with green. Look at that. Whoosh, look at that. And then we'll draw this with fill with, no, it won't be fill. We'll just make it black. Oh, yeah. All right. The class has 30 students. 20 students are in band, 15 are in art. So we have band and art. And 8 students are in both band and art. So filling out the Venn diagram, what goes in the center? 8. How many are in band over here? 12. How many are in art over here? 7. How many are left in the universe? 3. Yeah. Here's 20, 27, 30 total, so it's 3 left. All right. How many people are only in band? 12. 12. How many are only in art? 7. How many students are neither in band nor art? 3.